Hold a grain of sand at arm's length. That tiny patch of sky contains 10,000 galaxies. Every galaxy, billions of stars. The entire sky holds 13 million such grains. James Webb just looks deeper. In a field 3 times the width of the full moon, it catalogued nearly 800,000 galaxies. But it is now finding galaxies that existed 280 million years after the Big Bang, already massive and mature, when the universe should have been barely an infant. Today we witness the birth of galaxy clusters, map the invisible scaffolding of the cosmos, and face a universe 2 trillion galaxies wide. If this moves you, subscribe. Prepare yourselves. We begin. The James Webb Space Telescope had been in orbit for exactly 6 months when scientists pointed it at a patch of sky they had studied many times before. The target was a galaxy cluster called SMACS 0723, located about 4 billion light-years from Earth. It was a well-mapped cluster, nothing especially mysterious about it, a dense collection of galaxies bound together by gravity. The science team did not choose it for what it was. They chose it for what it could do. A single 12.5-hour exposure revealed something that stopped the room cold. When the image appeared on screens at the Space Telescope Science Institute on July 12, 2022, researchers were looking at thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Not just the cluster itself, but galaxies behind it, billions of light-years deeper into the universe. Some of those background galaxies had been smeared and stretched into luminous arcs by the gravity of the cluster in the foreground, a phenomenon called gravitational lensing that Einstein predicted more than a century before it was ever photographed. The cluster had bent the light from those distant galaxies like a curved lens bends light on a tabletop, amplifying it, bringing faint objects into view that would otherwise be completely invisible to any telescope humanity has ever built. That 4 billion light-year collection of galaxies had become a natural magnifying glass, and through it, Webb could see deep into the early universe with a level of infrared detail no instrument had ever achieved. Scientists who spent decades working toward that moment described standing in that room as a kind of disorientation. The image contained galaxies at every scale, from relatively nearby objects showing clear spiral arms to tiny, ancient smudges at the very edge of what light has had time to deliver to us. Some of those smudges existed when the universe was less than 1 billion years old. A few appeared to go back even further than that. The director of the National Aeronautics and Space Administration, Bill Nelson, presented the image to the President of the United States before the public release. He described it as the deepest view of the universe ever captured. He was correct. At that moment, what the image proved was not merely that the telescope functioned as designed. It demonstrated that Webb was operating far beyond its minimum requirements, collecting light with a precision and sensitivity that exceeded the most optimistic engineering projections. Scientists had planned for a machine that would push the boundaries of the observable universe. What they received seemed to belong in a different category altogether, and yet, as extraordinary as that first image was, it covered only a fraction of what teams had already been designing for years. Researchers around the world had spent the better part of a decade arguing over observing time, negotiating access, and mapping out which patches of sky deserved the attention of the most expensive scientific instrument ever launched into space. The first deep field was, in a sense, the opening seconds of a far longer investigation. Scientists already knew the real revelations would arrive when the telescope moved beyond one cluster examined for half a day and turned toward a broader stretch of the universe observed for weeks at a time. The numbers they would eventually pull out of those wider surveys would force a reckoning with everything cosmologists thought they understood about how galaxies form, and the scale of that reckoning would turn out to be unlike anything the field had prepared for. The story of how humanity began to grasp the true scale of the galaxy-filled universe starts with a decision that seemed, at the time, almost reckless. In December 1995, astronomers pointed the Hubble Space Telescope at a patch of sky in the constellation Ursa Major that contained no bright stars, no known galaxies, no known objects of any kind. just an empty-looking rectangle of darkness. They kept it pointed there for 10 consecutive days. What came back from that observation changed the way science thought about the universe. Within that patch of sky, so small that you could cover it completely by holding a single grain of sand at arm's length, researchers counted approximately 3,000 galaxies. Each one of those galaxies contained hundreds of billions of stars. Each one had been there, waiting, in a direction everyone had assumed was empty. The original Hubble Deep Field covered about a millionth of the total sky. Scientists repeated the observation at higher sensitivity in later years in a project known as the Hubble Ultra Deep Field, and the count in that tiny window climbed to approximately 10,000 galaxies, 10,000 separate island universes, each comparable in scale to our own Milky Way, all crammed into a patch of sky the size of a 1 millimeter square held at arm's length. Then came the arithmetic that genuinely disturbed people. The full sky contains room for about 13 million patches that size. If each patch holds roughly 10,000 galaxies, then a rough extrapolation puts the total galaxy count somewhere between 100 billion and 200 billion. That was the figure that sat in astronomy textbooks for about 2 decades. It felt unimaginable. It was also, as later work would reveal, a dramatic undercount. The point of the grain of sand exercise is not the final number. The point is the feeling that comes from holding that grain of sand between your fingers and understanding what it covers. Every direction you look, in any patch of sky you can imagine, galaxies stretch behind galaxies for billions of light years. The darkness is not empty, the darkness is full, and most of what fills it is invisible to any instrument we have ever built. James Webb was designed specifically to see what Hubble could not. The telescope operates primarily in infrared light, which allows it to penetrate the dust and cosmic redshift that renders the most ancient galaxies invisible to instruments built for visible wavelengths. Engineers knew before launch that a deep field observation with Webb would go further back in time and further down in brightness than anything previously attempted. What they underestimated was how quickly those observations would overwhelm the predictions. The Hubble Deep Field took 10 days to reveal 10,000 galaxies. The first Webb Deep Field image, a single 12.5-hour exposure, showed thousands of galaxies and structures the Hubble era had never hinted at. And the Webb telescope was just getting started. Astronomers had already drawn up plans for something far larger, a survey that would cover an area 3 times the size of a full moon, reaching infrared depths no survey had ever attempted. When that survey's data finally began arriving, the numbers inside it would make even the Hubble Ultra Deep Field seem, by comparison, like a glance through a keyhole. Designing the largest survey ever attempted with the most expensive telescope ever built is exactly as complicated as it sounds, and the arguments over how to do it went on for years before the first pixel was captured. The survey, eventually known as Cosmos Webb, emerged from a competitive process in which research teams around the world submitted proposals for how the James Webb Space Telescope's first cycle of general observations should be allocated. Time on the telescope is measured in hours, and those hours are genuinely finite. Every hour spent on one target is an hour not spent on something else. The teams making the case for a massive wide-field survey had to convince the scientific community that covering a large area of sky in detail was worth the cost of everything they would not be observing. They were granted 255 hours. The co-principal investigators, Jehan Kartaltape of the Rochester Institute of Technology and Caitlin Casey of the University of California, Santa Barbara, led a team that mapped an area of sky roughly 3 times the size of a full moon. They used Webb's near-infrared camera to cover 0.54 square degrees of the cosmos field, a patch of sky in the constellation Sextans that had been studied by dozens of telescopes over the previous 2 decades and was chosen specifically because so much prior data already existed to compare against. The technique required stitching together more than 10,000 individual images into a single coherent mosaic. The process took years of calibration, testing, and refinement even before the telescope launched. The data itself arrived in waves, each one requiring enormous computational effort to process and merge with what came before. In June 2025, the team released the full Cosmos Webb 2025 catalogue. It contained nearly 800,000 galaxies, each detected across 37 photometric bands, meaning each galaxy was measured at 37 different wavelengths of light. The combination of those measurements allowed researchers to estimate not just where each galaxy was in the sky, but how far away it was, how old its stars were, how fast it was forming new ones, and how much dust it contained. Maximilian Franco of the University of Paris-Saclay, who led the imaging analysis, described the experience of watching previously invisible galaxies appear on the screens for the first time. He said it was incredible to reveal objects that had been entirely hidden at other wavelengths, and deeply gratifying to finally see them show up on the computers after years of preparation. The scale of the catalogue is genuinely difficult to hold in the mind all at once. 800,000 galaxies, each one containing hundreds of billions of stars. If you printed the Cosmos Webb mosaic at the density of a standard newspaper, the image would stretch across a surface the size of a full football pitch. Every smear, every blur, every barely resolved speck in that newspaper would be an entire galaxy. The survey spans cosmic history, from objects relatively nearby to galaxies that existed when the universe was barely 7% of its current age. In a single mosaic, researchers captured most of the 13.8 billion years that the observable universe has been in existence. And the scientists who built the catalogue already knew that the most surprising things inside it had not yet been found. Behind every landmark scientific achievement, there is a team of people who spent years solving problems that will never make the headlines, and the Cosmos Webb catalogue is no exception. The act of turning 10,000 raw telescope images into a coherent scientific catalogue is not glamorous work. It involves identifying and removing artifacts created by cosmic rays, striking the telescope's detectors, correcting for the fact that each of the 37 photometric bands was observed at slightly different times and with slightly different instrument configurations, and building a consistent coordinate system so that a galaxy appearing in one filter matches precisely with its counterpart in all the others. A single mismatch in alignment, even by a fraction of an image pixel, can corrupt the measurement of an object's color, and a corrupted color measurement can produce a completely wrong distance estimate. Marco Shuntov of the Cosmic Dawn Center in Copenhagen led the effort to construct the catalogue itself. The catalogue, known as Cosmos Webb 2025, is what transforms a mosaic of images into a scientific tool. Each of the nearly 800,000 entries represents a galaxy with a set of measured properties: position, brightness, in each of the 37 bands, estimated distance, estimated stellar mass, estimated star formation rate, and several dozen additional parameters. The catalogue is what allows researchers around the world, many of whom had nothing to do with the original survey, to ask questions of the data and find answers. Maximilian Franco handled the imaging pipeline, the sequence of computational steps that produce the final calibrated images from the raw detector readouts. He described the challenge of revealing galaxies that were invisible at every other wavelength, objects that appeared only when the deep infrared sensitivity of the Webb telescope was applied. Some of those galaxies had been present in prior surveys of the cosmos field as faint smudges, or had been entirely absent. In Webb's infrared data, they emerged with detail that prior generations of astronomers had no way to anticipate. The team combined observations not just from Webb's near-infrared camera but from multiple instruments, including the mid-infrared instrument, as well as archival data from the Hubble Space Telescope, the Subaru telescope on Mauna Kea, and the Very Large Telescope in Chile. The layering of all those observations, each covering different wavelength ranges and different depth limits, produced a picture of the galaxy population across cosmic time richer than any previous dataset. The survey covers galaxies from redshift 0.1, objects relatively close on a cosmic scale, all the way to redshift 12, which corresponds to galaxies that existed when the universe was roughly 3% of its current age. That range means the catalogue spans essentially the entire history of visible structure in the universe, from relatively mature galaxies forming stars today to the first recognizable predecessors of modern galaxy clusters. The scientific papers emerging from Cosmos Web in 2024 and 2025 are rewriting multiple chapters of galaxy formation theory simultaneously. What the architects of the map knew, and what they had been careful not to say too loudly until the data confirmed it, was that the catalogue contained objects with no explanation in the standard models. Galaxies that were too massive, too luminous, and too mature to have formed in the time available. The map had been built. Now came the harder work of understanding what it was actually showing. While Cosmos Web was being designed to cover as much sky as possible, a separate team took the opposite approach. They chose one target, one of the most extreme objects in the nearby universe, and stared at it until it revealed things no other method could reach. Abel 2744 is known among astronomers as Pandora's Cluster, a nickname earned because every time scientists look at it carefully, they find something unexpected inside. It is a merging system, several massive galaxy clusters that collided and are still in the process of entangling, their gas clouds slamming together at millions of miles per hour, while their galaxies and dark matter halos interpenetrate in a gravitational collision that has been ongoing for billions of years. The result is an object of almost unparalleled mass, concentrated in a relatively small region of sky. That mass makes it one of the most powerful natural lenses in the observable universe. A survey called the Ultra-Depth Near-Infrared Spectrograph and near-infrared camera observations before the epoch of Ryanization, which its teams shortened to UN-COVA, targeted this cluster specifically because of what its gravity could do to light coming from behind it. The lensing from Pandora's cluster is not uniform. The multiple merging subclusters create overlapping zones of gravitational distortion, each one bending light from different directions and at different magnifications, essentially creating dozens of separate gravitational lenses stacked on top of each other. The UNCOVA team achieved observation depths of approximately 32 magnitudes in the lensed region, meaning the faintest objects they detected were emitting so little light that without the cluster's amplification, no telescope built by humanity could have seen them. In practical terms, the cluster was acting as an additional telescope, hundreds of meters in diameter, stacked on top of Webb's own 6.5-meter primary mirror. Spectroscopic follow-up, which involves dispersing an object's light into its component wavelengths to measure its distance precisely, was obtained for nearly 700 objects within the survey area. Those objects ranged from galaxies at redshift 0.3, relatively nearby on a cosmic scale, to objects at redshift 13, which places them in the universe's first few 100 million years. What emerged from that spectroscopic campaign was a picture of galaxy evolution spanning nearly the full history of the observable universe, all captured through a single extraordinary lens. Some of the most distant objects in the UNCOVA sample were completely undetected in prior surveys, including observations made by the Hubble Space Telescope over multiple decades. They existed in deep data, invisible, waiting for an instrument sensitive enough and a natural lens powerful enough to bring them to the surface. The extreme magnification available through Pandora's cluster also allowed scientists to study the internal structure of early galaxies in detail that is impossible in unlensed fields. They could measure star formation rates in individual regions of a galaxy that existed when the universe was less than 5% of its current age. They could see whether those galaxies had central concentrations or were more diffuse. They could begin to ask whether the structures forming in the first billion years resemble the structures visible today. The answer, in many cases, was that they do not, and the reasons why are still being argued in seminars around the world. The name comes from an Old English word meaning rising light, and it was chosen deliberately because the object it describes arrived at humanity's instruments after a journey of nearly 13 billion years. Earendel is a star. A single star, or what appears to be one, located in a galaxy called the Sunrise Arc at a redshift of approximately 6.2. To put that in terms of cosmic time, The light from Earendel left its source when the universe was less than 1 billion years old, at a point when the first generations of massive stars were living and dying at extraordinary rates, seeding the cosmos with the heavy elements that would eventually make planets like Earth possible. It should be invisible. Individual stars at that distance produce so little light that even the James Webb Space Telescope, the most sensitive instrument humanity has ever built, cannot normally detect them. The nearest stars outside our galaxy are already at the edge of individual stellar resolution for the most powerful ground-based telescopes. The idea of detecting a single star billions of light-years away, in the era before the universe had finished becoming transparent, seemed physically impossible for most of the 20th century. What made Earendel visible was a coincidence of geometry so precise that scientists initially struggled to accept it. The sunrise arc is located behind a galaxy cluster called WHL 0137, which sits about 5.5 billion light-years from Earth. That cluster bends and amplifies light from the galaxy behind it, just as Pandora's cluster amplifies its background objects. But at the moment, astronomers observed Earendel with the Hubble Space Telescope in 2022, something extraordinary was happening. The star happened to be aligned almost exactly on the gravitational caustic of that cluster, the line of maximum magnification where the lensing effect is strongest. At that alignment, the amplification of Earendel's light reached levels that made the observation possible. Estimates of the true magnification varied widely, but the enhancement was enormous, potentially tens of thousands of times. That amplification is what made a star from the first billion years of the universe detectable by instruments in orbit around a planet that did not yet exist when the star was shining. Follow-up observations with the James Webb Space Telescope measured the star's spectrum more precisely. What came back was not the clean signature of a single hot star. The data suggested something more complex, possibly a binary system, 2 stars orbiting each other, with temperatures ranging from roughly 9,000 to 34,000 Kelvin. The cooler of the two would be a star comparable to some of the most massive stellar objects known in the local universe. The hotter would be something at the upper limit of stellar temperatures. For the moment of its discovery, Earendel held the title of the most distant individual stellar object ever resolved by human instruments. Then, in 2025, a paper appeared that questioned everything the field had concluded about what Earendel actually was. The challenge did not come from outside the scientific mainstream. It came from a team with direct access to the same James Webb Space Telescope data, and the argument they made was detailed, methodical, and not easy to dismiss. Massimo Pascali and colleagues at the University of California, Berkeley, published their challenge in the Astrophysical Journal Letters in July 2025, and the central claim was straightforward to state, even if the implications took longer to absorb. What if Earendel is not a single star at all? The alternative they proposed was that the object is a compact, ancient cluster of stars, specifically a metal-poor globular cluster progenitor, one of the dense, tightly bound collections of hundreds of thousands of stars that formed in the earliest galaxies, and whose descendants orbit the Milky Way today as the ancient globular clusters visible through any backyard telescope. If this interpretation is correct, the most distant individual stellar object ever detected is actually a compact stellar system, not a lone star. The argument rested on several lines of evidence assembled from James Webb Space Telescope spectra and from comparisons with other objects along the same gravitational arc. The first line of evidence involved metallicity, the abundance of elements heavier than hydrogen and helium detectable in the object's light. Earendel's spectral properties match the range expected for very metal-poor stellar populations, which is consistent with globular cluster progenitors from the early universe, but does not on its own distinguish between a single star and a dense cluster of them. The more pointed argument came from comparing Earendel to another source in the same lensed arc, a separate object whose angular size and brightness had already led researchers to identify it as a star cluster. Earendel, Pascali's team argued, shares enough properties with that confirmed cluster, in terms of its stellar surface density, its age estimates, and the behavior of its brightness across different wavelengths, that the simpler explanation is that both objects belong to the same category. The key word in that argument is simpler. The gravitational magnification that made Earendel visible is extreme, but extreme magnification also comes with large uncertainty in the exact amplification factor. If the true magnification is on the lower end of the estimated range, a single star would produce far too little light to account for what Webb detected. A compact cluster of 1 million or more stars, even at very low metallicity, would have no such problem. Scientists working on Earendel responded that the question remains unsettled. The magnification estimates carry enough uncertainty to allow for both interpretations, and other features of the data are easier to explain with a single stellar source. The debate continues, and the final answer requires additional observations not yet scheduled. What is certain, regardless of the outcome, is the window Earendel opens into the early universe. Whether the object is a single massive star or a compact precursor to the kind of globular clusters orbiting ancient galaxies today, it represents a measurement at a distance and an epoch that would have seemed like science fiction 20 years ago. The frontier of individual stellar detection has been pushed to a place in the universe where the very first stars were forming. And in 2024, a separate team had already found something in that same early universe that would, in some ways, be even more astonishing. Angela Adamo spent years preparing for what she would see when the James Webb Space Telescope images of a specific lensed galaxy arrived on her computers. She was still astonished. Adamo leads a research group at Stockholm University focused on how star clusters form, grow, and survive across cosmic history. Her team had targeted a gravitationally lensed galaxy called SPT-0615 behind a foreground cluster that sits at a redshift of approximately 10.2. That redshift places the background galaxy 460 million years after the Big Bang, in the thick of the earliest period of organized star formation in the observable universe. The lensing magnification was high, and Webb's resolution was sufficient to peer into the galaxy's interior at scales that no prior observation could achieve. When the images processed through the pipeline and the team sat down to examine them, Adamo has described the experience as a chain of small shocks arriving in rapid succession. Inside a region spanning less than 230 light-years across, the team resolved 5 compact objects. 5 separate, distinct concentrations of stars, each one spanning only about 3 light-years in intrinsic size, each one packed with approximately 1 million stellar masses. Those 5 objects are now called the Cosmic Gems Arc. The results were published in the journal Nature in June 2024. The density of these clusters is the number that most clearly communicates what makes them extraordinary. Star clusters in the nearby universe, including the younger ones forming in active star-forming galaxies today, have stellar surface densities ranging from a few hundred to a few thousand times the mass of our nearest star per square light-year. The cosmic gems clusters have stellar surface densities 1,000 times higher than the densest young star clusters observed anywhere in the local universe. They are packed to a degree that appears essentially nowhere in the galaxy population around us today. At those densities, something interesting and potentially important happens. Massive stars crowd together closely enough that they interact gravitationally on timescales shorter than their individual stellar lifetimes. Runaway mergers become possible, where star after star falls into a growing central mass, accumulating until the product is something too massive to have formed through ordinary stellar evolution. That pathway is one proposed mechanism for creating intermediate mass black holes, whose existence has long been suspected but whose formation process has never been directly observed. The cosmic gems clusters are younger than 50 million years, measured from their stellar populations. Their metallicity is less than 1% of the metallicity of our own galaxy, consistent with objects forming in the earliest stages of chemical enrichment in the universe. Their masses and densities match what theorists have long predicted the ancestral globular clusters should look like before billions of years of dynamical evolution thinned and softened them into the ancient systems orbiting the Milky Way. Today, Larry Bradley of the Space Telescope Science Institute who contributed to the analysis, noted that no other telescope could have made this discovery. That statement is accurate. Without the combination of Webb's infrared sensitivity and the cluster's gravitational magnification, these 5 objects would remain invisible, embedded in data we would never know how to read. What those 5 clusters represent is the possibility of watching the birth of structures that have been with us in evolved form for the entire history of the galaxy. And from objects born 460 million years after everything began, the story was about to leap forward in time to something far larger in scale. The cosmic vine was hiding in data from a survey called the Cosmic Evolution Early Release Science Field, buried inside a catalogue of galaxy redshifts that researchers were still working through in late 2023. What Shuowen Jin and colleagues at the Cosmic Dawn Center in Copenhagen were looking for was any pattern in the redshift distribution that might indicate galaxies clustering together at the same distance. The technique is straightforward in principle. If you measure the spectroscopic distance to hundreds of galaxies in the same patch of sky and find that many of them fall at almost exactly the same redshift, you are likely looking at a structure rather than a random assembly. Galaxies at the same redshift are at the same distance. Galaxies at the same distance that appear close to each other in the sky are, in 3 dimensions, genuinely close to each other in space. What Jin found was 20 galaxies with confirmed spectroscopic redshifts, all clustered between redshift 3.434 and redshift 3.45. That places them about 2 billion years after the Big Bang, in a period when galaxy formation was intensely active and when the largest structures in the universe were still assembling from smaller components. But 20 galaxies is just the confirmed core. Additional analysis identified approximately 200 candidate members surrounding that core, spread across a region of the sky that, when translated into physical distances at that redshift, produced a structure roughly 13 million light-years long and only about 650,000 light-years wide. The shape is what earned it the name. The 20 confirmed galaxies and their surrounding cloud of candidates trace a long, narrow filament, like a vine extending across the early universe, with the 2 most massive galaxies sitting near its center. Those 2 central galaxies are each about 800 billion times the mass of our nearest star. That is an enormous stellar mass for objects that existed only 2 billion years after the Big Bang. But the mass is not what surprised the team most. What surprised them was that both galaxies had already stopped forming stars. In an environment teeming with activity, in a large-scale structure actively accumulating mass and surrounded by hundreds of star-forming galaxies, the 2 biggest members of the vine had already gone quiet. Their stellar populations were old, their star formation rates were effectively 0, and their shapes were dominated by central bulges rather than extended disks. They looked, in other words, like the old, red, elliptical galaxies common in massive clusters in the nearby universe today. The nearby universe is 13.8 billion years old. These galaxies had reached that state in just 2 billion years. The simulations that cosmologists run to predict large-scale structure suggest that the cosmic vine will continue to evolve, pulling in more material from its surrounding environment, eventually collapsing into a virialized galaxy cluster with a total mass exceeding 100 trillion times the mass of our nearest star, comparable in scale to the great clusters visible nearby in the modern universe. That collapse has not yet happened in any telescope we have. What we are seeing in the James Webb Space Telescope data is the process mid-formation, already producing surprises no model anticipated. And 2 billion more years deeper into the past, something even larger was already under construction. In January 2026, a paper appeared in the journal Nature that described something astronomers had thought they would not find for many more years. The team was led by Akos Bogdan of the Center for Astrophysics at Harvard and Smithsonian. The object they were reporting on was a protocluster, a galaxy cluster in the process of forming, located 12.7 billion light-years from Earth. At that distance, the light arriving in Webb's detectors left its source when the universe was just barely over 1 billion years old. The structure is called JWST ID1, and it may be the most distant confirmed galaxy cluster core ever detected. It contains at least 66 potential galaxy members visible in James Webb Space Telescope imaging, a dense concentration of galaxies in a relatively compact region of sky. Its total mass, including the dark matter halo in which those galaxies are embedded, is estimated at approximately 20 trillion times the mass of our nearest star. That is not the mass of one large galaxy. That is the mass of an entire galaxy cluster, assembled when the universe was less than 8% of its current age. But the mass alone was not what made JWST the subject of urgent scientific discussion. What made it front-page news in the astrophysics community was what the Chandra X-ray Observatory detected when it was pointed at the same location. Chandra sees the universe in X-ray light, the extremely high-energy radiation produced by matter heated to temperatures of millions of degrees. Galaxy clusters, when they reach sufficient mass, contain enormous quantities of gas that has fallen toward the cluster's center and been shock-heated to those extreme temperatures. This hot, glowing gas fills the space between galaxies in a mature cluster and produces a characteristic X-ray signature that allows astronomers to confirm that a cluster's mass is genuinely concentrated and gravitationally bound, rather than a chance alignment of unrelated objects at different distances. Chandra detected that signature at the location of JWST, a cloud of gas heated to millions of degrees sitting inside the structure, confirming that the cluster is real, that its mass is genuinely concentrated, and that the physical processes of cluster assembly are already well underway. The problem is that standard models of cosmological structure formation predict galaxy clusters of this mass should not begin appearing until the universe is significantly older. The timeline for assembling 20 trillion stellar masses into a bound gravitationally virialized structure requires conditions that, according to those models, did not yet exist at the epoch of this cluster's observation. Bogdan described the finding as evidence that the universe was in a significant hurry to grow up, using a phrase that captured a feeling widespread in the observational community by early 2026. His co-author, Gerrit Schellenberger, offered a different image. He compared the observation to watching an assembly line build a car, rather than trying to figure out how a car works by examining only the finished product. The cluster was being assembled in front of the telescope, in real time, over 12.7 billion years of delay. What JWST revealed was that the scale of structure in the early universe was not just surprising at the level of individual galaxies, it was surprising at the level of the largest gravitationally bound objects that exist. A discovery like this one does not stand alone. It connects to a growing pattern in the data, a pattern suggesting that something in our understanding of cosmic origins is fundamentally incomplete. And the most dramatic piece of that pattern was still waiting to be introduced. For a brief window in the spring of 2024, a galaxy from the JADE survey held the title nobody expected to exist: Most Distant Confirmed Galaxy in the Known Universe. A genuine record from the edge of everything detectable. Scientists had been stunned by its existence. The instruments had checked and rechecked. The data held. Then, 12 months later, someone beat it. In May 2025, a team at Yale University announced the discovery of a galaxy that pushed further back in time than anything before it. Its designation was MOME Z14, short for Mother of Miracles, drawn from the survey that found it. When you understand what it represents, that name feels exactly right. Its light left the galaxy 280 million years after the Big Bang. It had been traveling toward us for 13.5 billion years. Peter van Dokkum, professor of astronomy and physics at Yale, led the team that pulled it from the data. The galaxy had been hiding inside the enormous Cosmos Webb mosaic, waiting to be found. Its signature was unmistakable once you knew what to look for. Short wavelengths of light, the kind produced by hydrogen gas, had been completely absorbed by the ancient neutral gas surrounding the galaxy before it could escape into open space. The galaxy appeared bright in longer infrared wavelengths but vanished entirely in the blue ones. That dropout pattern is the fingerprint of extreme distance. Every galaxy at that depth wears the same disguise. MOME Z14 is tiny, only about 500 light-years across. For comparison, the Milky Way spans roughly 100,000 light-years. This galaxy could fit inside the space between our nearest few hundred star clusters and disappear. Yet somehow, from that impossibly compact volume, it blazes across 13.5 billion years of space and arrives at Webb's mirror still detectable. That brightness requires either an extraordinary concentration of forming stars or something else entirely. When the team checked for signs of a central supermassive black hole feeding on surrounding gas and contributing its own light, they found nothing. This galaxy's luminosity comes entirely from stars being born at a furious rate. Van Dockum gave an interview after the announcement and reached for a comparison to make the timescales tangible. Sharks, he pointed out, have been swimming in Earth's oceans for longer than the age of this galaxy at the time its light was emitted. The ocean predators that predate every major mass extinction in Earth's history represent a longer stretch of continuous survival than the entire lifespan of MOMEM. Z14, at the moment Webb photographed it. That comparison lands differently than most astronomical metaphors. It locates deep time inside something living and breathing, rather than something geological and cold. Van Dockum added a remark that should stop you in your tracks. Webb, he said, was not supposed to discover any galaxies this early in the universe's history, not at this point in the mission. The discovery pipeline had been designed around expectations of scarcity at extreme distances. The expectations, one after another, have been shattered. By early 2026, more than 100 galaxies similar to MOEM Z14 had been catalogued from just the first 400 million years after the Big Bang. The number grows with every new pass through Webb's data. Astronomers expected a handful of faint, primitive smudges from this era. They are finding something that looks increasingly like a crowd, and that crowd is doing something the entire theoretical framework of modern cosmology was designed to prevent. The oxygen should not have been there. That was the first reaction from Sander Schau's of Leiden Observatory when the data came through from the ALMA radio telescope array. The measurement showed 10 times more oxygen than any reasonable model predicted a galaxy could have produced in the short time it had existed. The result arrived in early 2025, published simultaneously by two independent research teams who had reached the same conclusion working from the same data through completely separate methods. The confirmation from two groups at once made the result essentially impossible to dismiss. To understand why oxygen is so extraordinary at this distance and depth, you need to understand where oxygen comes from. It is forged inside massive stars through nuclear fusion. The Big Bang produced hydrogen and helium almost exclusively. Every atom of oxygen in your body, in Earth's oceans, in the air you breathe, was made inside a star that lived and died before our solar system formed. When a massive star exhausts its fuel and explodes as a supernova, it scatters those freshly forged heavy elements back into surrounding space. The next generation of stars, and eventually planets, forms from that enriched material. That process takes time. Stars must be born. They must burn through their fuel, which takes millions to tens of millions of years, even for the most massive ones. Then they must die and explode and spread their contents. Then the next generation must form. For a galaxy that existed only 290 million years after the Big Bang to show 10 times more oxygen than expected, multiple complete cycles of stellar birth and death had already happened inside it. Multiple generations of massive stars had lived and died, each one enriching the raw gas available to the next generation, each death seeding the galaxy with heavier elements. Schau's described the discovery as finding an adolescent where you would only expect babies. The galaxy was already chemically mature in an infant universe. The second team, led by Stefano Carniani of the Scuola Normale Superiore in Pisa, published their complementary result at the same moment. They were equally astonished. The evidence, Carniani said, opened a new view on the first phases of galaxy evolution that nobody had been prepared for. A galaxy could become this chemically advanced this fast. The enrichment that took the Milky Way billions of years to accumulate had already happened, at fraction of that time, inside this compact, blazing structure. There is a precision detail here that deserves its own moment. The ALMA measurement of the galaxy's distance achieved accuracy to within a fraction of a percent. That is the equivalent of measuring a distance of 1 kilometer and being accurate to within 5 centimeters, at 13.5 billion light-years. With a radio telescope on the ground, what this detection forces onto the table is a problem far larger than one galaxy. If that ancient object was already chemically mature before the universe was 300 million years old, then the stars responsible for all that enrichment had to be forming, living, and dying in the first 200 million years or less. The very first sliver of cosmic time, that pushes the opening act of stellar history far earlier than any model predicted. And that is when the crisis in cosmology stops being about individual galaxies and starts being about the entire framework. The standard cosmological model is one of the most successful scientific theories ever constructed. It describes how the Big Bang produced a nearly uniform universe, how tiny quantum fluctuations in density grew into seeds of structure, how gravity amplified those seeds into clumps of dark matter, how gas fell into those clumps and fragmented into the first stars, and how those stars gathered into the first galaxies hundreds of millions of years later. The model is supported by decades of observation and makes accurate predictions across an enormous range of cosmic scales. Most cosmologists regard it as one of humanity's crowning intellectual achievements. Webb has spent 3 years finding things the model says should not exist. The problem began accumulating before MOME Z14. As the telescope turned toward deep fields and gravitational lenses and began cataloguing galaxies at extreme distances, a pattern emerged. The galaxies being found were too massive, too bright, too chemically evolved. They contained too many stars for their age, too much enrichment, too much organized structure. At every distance where the model made confident predictions about what should be there, Webb kept finding something more. Michael Boylan-Colchin of the University of Texas at Austin ran the numbers carefully and published the result. Some of the massive galaxies Webb found at the highest redshifts require star formation efficiencies of 50% or higher to have assembled their stellar mass in the available time. In the present-day universe, the fraction of available gas that actually converts into stars typically sits between 1 and 5%. The standard model predicts a theoretical maximum of 10 to 20% under the most favorable conditions ever modeled. To reach 50% requires conditions that the existing framework has no mechanism to produce. Some galaxies, Boylan-Colchin calculated, appear to need efficiencies approaching 100%. Every available atom of gas converted into stars, almost instantaneously on cosmic timescales, with no waste, no suppression, no physical process slowing the conversion down. The known laws of star formation should make that impossible. Supernovae alone should disrupt a galaxy's gas supply long before efficiency approaches those levels. The problem has another dimension beyond efficiency. These galaxies are enormous. Their stellar masses are hundreds of millions to billions of times the mass of a typical star. Assembling that much stellar mass in 200 million years requires a rate of star formation so extreme that it strains every calibrated measurement astronomers have from the local universe. Webb was designed to see far. What it has seen is raising questions that push well beyond its engineering specifications. What is happening in the early universe that we have failed to model? And is the model in need of adjustment? Or is it in need of something more drastic? When the impossible galaxies kept appearing, cosmologists did not abandon their framework immediately. That would have been premature. Instead, they began proposing mechanisms that could explain the observations within, or just slightly beyond, the boundaries of existing theory. And the resulting list of candidates is more interesting than any single answer would have been. The leading explanation is called feedback-free star formation. In today's universe, massive stars are extraordinarily disruptive. They blast out radiation that ionizes surrounding gas. When they die in supernova explosions, the shock waves heat their surroundings and push material away from regions where new stars might form. This feedback process is essentially self-limiting. Stars form, become destructive, and slow down the formation of more stars around them. In the very early universe, the conditions may have been different in a specific and important way. The first galaxies formed from gas with almost no heavy elements. Metal-free gas cools and fragments differently. Some theoretical models suggest that in this window, galaxy-scale star formation could proceed at efficiencies approaching the theoretical maximum before the disruptive effects of the first supernova explosions could propagate through the host galaxy. The feedback loop existed, but it had not had time to engage. A second proposed explanation involves the nature of the first stars themselves. The very first generation, formed from pure hydrogen and helium, may have been far more massive than typical stars today. More massive stars produce more ultraviolet light per unit of mass. If early galaxies were dominated by these enormous first-generation stars, the galaxies would appear far brighter and more massive than they actually were. Webb might in some cases be detecting an optical illusion, a galaxy whose apparent luminosity is inflated by a stellar population unlike anything in the modern universe. A third possibility involves contamination from actively feeding supermassive black holes. Some impossibly luminous galaxies may contain compact central black holes consuming surrounding gas and adding their own intense radiation to the galaxy's total light output. Follow-up studies have confirmed this for some of the most extreme cases. It does not account for all of them. A fourth candidate involves the absence of dust. Early galaxies may have contained far less dust than modern ones. In the present universe, dust absorbs a significant fraction of the ultraviolet light that newly formed stars produce. If early galaxies were effectively dust-free, that light escaped freely, making those galaxies appear more luminous than their true star-forming rates would justify. A minority of theorists have proposed something more fundamental: modifications to the behavior of dark matter or dark energy in the early universe that would allow structure to grow faster than the standard framework predicts. These proposals face serious constraints from other observations. None of these explanations is fully satisfying on its own. The truth likely involves several acting together, but before anyone declares the crisis resolved, the skeptics have something essential to say. Science advances by subjecting its most dramatic claims to relentless pressure until only the ones that survive remain standing. The impossible galaxies are no exception, and the scrutiny they have received over the past 3 years has already revised some of the most extreme initial announcements downward. Most cosmologists working in this field do not believe the standard model is broken. They believe it is under stress. They believe our understanding of early star formation physics is incomplete. They also believe, based on years of experience with Webb data, that some fraction of the most alarming early claims will prove to have been overstated. That revision process has already begun. In the first 2 years of Webb operations, several galaxies announced with great fanfare as extraordinary distance records were later found to have been misidentified. The technique used to estimate galaxy distances from imaging data alone, called photometric redshift modeling, works by matching the brightness of a galaxy across multiple wavelengths to a library of theoretical templates. It is powerful and often accurate. It is also fallible in ways that matter enormously at extreme distances. A galaxy at a relatively modest distance that happens to be very red can mimic the dropout signature of an extremely distant galaxy in certain filter combinations. When spectroscopic follow-up, which directly measures the wavelengths of specific atomic emission lines and produces far more reliable distance estimates, was applied to some early high-profile candidates, the distances came back dramatically lower. This is the process working as designed. Photometric redshifts are screening tools. Spectroscopy is confirmation. The genuine distance records that remain standing, the ones that have survived spectroscopic verification, are locked in. The rest were drafts, not discoveries. The deeper theoretical gap deserves honest assessment as well. The discrepancy between what the standard model predicts and what Webb observes is real. It is statistically significant. It has persisted as better data arrived. The gap could reflect the model's need for revision in its treatment of early star formation efficiency. It could reflect something more fundamental. It could also reflect selection effects, where Webb preferentially detects the rarest, brightest objects at extreme distances, while the more typical population at those redshifts remains too faint to catalogue. One published review from early 2026 summarized the expert consensus plainly. It is too early to claim the standard model is broken. The observations are extraordinary. The discrepancies are genuine. The work is continuing. Drawing final conclusions now would be premature. Science under pressure can look like crisis and later reveal itself as growth. That summary was written before one of the strangest and most philosophically striking results of the Webb era arrived in a journal. A result that showed, for the very first time, the invisible architecture holding everything together. Diana Scognamiglio had been working toward a map that should have been impossible to make. Dark matter emits nothing, reflects nothing, and absorbs nothing. It interacts with ordinary matter only through gravity. There is no camera that can photograph it, no spectrograph that can fingerprint it, no wavelength of light it produces for any detector to catch. Every dark matter map ever made has been a reconstruction, an inference drawn from the gravitational effects dark matter leaves on things that can be seen. For years, those reconstructions had been blurry. Scognamiglio, a researcher at NASA's Jet Propulsion Laboratory, wanted to change that. In January 2026, the result was published in the journal Nature Astronomy. It was the sharpest, most detailed map of dark matter ever produced from space-based observations, and it covered an area of sky roughly 2.5 times the size of the full moon. The map was built from the same Cosmos Webb survey data that had yielded MOMZ-14 and nearly 800,000 catalogued galaxies. Within that patch of sky, Scognamiglio's team used approximately 250,000 background galaxies as probes, tracing the distribution of invisible mass with a clarity no previous instrument had achieved over a comparable area. The numbers that describe this achievement require a moment of consideration. The map is twice as sharp as any previous space-based dark matter map produced at this scale. It traces mass concentrations corresponding to 129 galaxies per square arc-minute of sky, nearly double the density achievable by the Hubble Space Telescope. It reaches back to when the universe was approximately 3 billion years old, the peak era of cosmic star formation, and it resolves structures that previous maps had merged into featureless blurs. Scognamiglio described the experience of comparing this map to earlier versions as moving from a watercolor sketch to a high-resolution photograph. The structures were always there. Now their details are visible. When the first side-by-side comparison slide was shown at a Cosmos Research Collaboration meeting in May 2025, placing the older Hubble-era dark matter map of this region next to the new Webb-era version, the room did something unusual for a scientific conference. People started clapping. Scognamiglio later described it as recognition rather than celebration. Scientists saw something they had not expected to be achievable yet, and they responded the only way that felt appropriate. The map reveals a structure that has been theorized for decades but never seen at this resolution. A network, an architecture. The invisible skeleton on which every visible thing in the universe is arranged. And the moment you understand what that skeleton looks like and why it exists, the universe becomes a fundamentally different place to inhabit. Nothing in the universe falls where it falls by accident. Every galaxy, every cluster, every thread of stars connecting one dense node to another occupies the position it does because dark matter pulled the surrounding gas there first, quietly and invisibly, over billions of years. The dark matter map, built from Cosmos Webb data, reveals this scaffolding with enough clarity to see individual strands of the web, and understanding how the map was built is almost as striking as what it shows. The method is called weak gravitational lensing. Consider a galaxy 10 billion light-years away. Between that galaxy and Webb's mirror lies a vast, invisible architecture of dark matter distributed across hundreds of millions of light-years. None of it emits light. but its gravity bends the path of light passing through it, and that bending ever so slightly distorts the apparent shape of the distant galaxy as seen from Earth. The distortion is tiny, a fraction of a percent of the galaxy's total apparent size. On any single galaxy, the effect is completely undetectable against the natural variation in how galaxies are shaped. This is where statistics rescues the measurement. When you analyze 250,000 background galaxies simultaneously and search for coherent patterns in their distortions, the dark matter signal rises out of the noise. Galaxies positioned behind a dense region of dark matter are all distorted in a consistent direction. By mapping where these correlated distortions appear across the survey, you reconstruct where the invisible mass concentrations are located. You build a map of what cannot be seen from the echoes it leaves in what can. What the map shows is not a smooth, uniform distribution of dark matter. It shows peaks where galaxy clusters sit, their massive dark matter halos dominating the local gravitational landscape. Connecting those peaks, elongated filaments of moderate density stretching tens of millions of light years. Between the filaments, enormous voids, regions so deficient in mass that galaxies avoid them almost entirely. This is the cosmic web. Computer simulations had predicted its existence for 40 years. Galaxy surveys had traced its outlines through the distribution of visible matter. The January 2026 map is the first time its dark matter backbone has been resolved at this level of detail in a space-based observation, and the level of detail matters enormously. Faint galaxy groups previously invisible in earlier, blurrier maps now appear clearly. Filaments that had seemed to merge into one another, separate into distinct structures. The universe's hidden architecture is, at last, visible. Emily Liner of Illinois Institute of Technology captured the essential strangeness of this result. Dark matter, she noted, represents 85% of all the mass in the universe. We do not know what it is, and until very recently, we could barely see where it was. JWST has changed that, and what it shows is that the universe is organized rather than random, structured rather than scattered, woven rather than spilled. That organization is what makes the next number so hard to absorb. Christopher Consolis had a problem with the galaxy count, and the galaxy count had been wrong for over 20 years before he identified the error and fixed it. The original figure, somewhere between 100 and 200 billion galaxies in the observable universe, came from a calculation performed after the Hubble Space Telescope completed its deep field observations in the 1990s. Researchers counted the galaxies visible in a tiny patch of sky, applied that density to the full celestial sphere, and arrived at a number that seemed almost incomprehensibly large. 200 billion galaxies. The figure entered textbooks, scientific summaries, documentaries, and public consciousness as an established fact. Consolis, an astronomer at the University of Nottingham, spent years building three-dimensional models of how galaxy populations change through cosmic time, and recognized that the straightforward extrapolation from deep field images was missing something essential. The most distant, faintest galaxies in the early universe, the small, numerous objects that dominated the first billion years of cosmic history, were simply below the detection threshold of every telescope that existed. They were real. They were out there. They were producing light that crossed billions of light years to reach the vicinity of Earth, then stopped short of triggering any detector. They had never been counted. When Consolis's team published their revised calculation in 2016, the corrected total was closer to 2 trillion galaxies, 10 to 20 times higher than the previous estimate. More than 90% of all galaxies in the observable universe had been invisible to human instruments and therefore absent from every count. 2 trillion. Consolisa offered a comparison to give the number a human scale. 2 trillion is roughly the number of seconds in 1,000 average human lifetimes. Counting at 1 galaxy per second, without pause, without sleep, would take 63,000 years to reach 2 trillion. Human civilization, including all of recorded history from the earliest writing to the present day, is approximately 10,000 years old. The count would not be finished in the entire span of human civilization so far. Consolis noted at the time that JWST was the telescope most likely to begin revealing this hidden population. The Cosmos Web Catalog, with its nearly 800,000 galaxies spanning most of cosmic history, represents an early step in that direction. Extrapolate its galaxy density across the full sky, and you arrive at a number consistent with 2 trillion. More than 90% of those galaxies have never been seen by any instrument built by any civilization on this planet. Most have never been photographed. Most have never been named. Most will require telescopes that do not yet exist to detect at all. There are 2 trillion galaxies in the observable universe. Each one is a universe of its own, and every one of them is made of something that dwarfs every other quantity in this story. The number of stars in the observable universe resists intuition completely. It exceeds, by orders of magnitude, every quantity that appears in ordinary experience. It exceeds the national debt of any country by a factor that renders the comparison meaningless. It exceeds the number of cells in a human body by approximately 1 billion times. The conservative estimate is 10 to the 24th. Written in full as a word, that is 10 septillion, a 1 followed by 24 zeros. Astronomers arrived at this figure by combining the estimated number of galaxies with the estimated average number of stars per galaxy, accounting for the full spectrum of galaxy sizes, from massive spirals to small dwarf galaxies that make up the actual cosmic population. The comparison that gives this number shape involves sand. Every beach on Earth, every desert, every volcanic shoreline, every windswept dune and rocky tide flat collectively contains an estimated 7.5 times 10 to the 18th grains of sand. 10 septillion stars exceeds this total by roughly 1 million times. For every single grain of sand on every beach and desert on the entire surface of the planet, there are approximately 1 million stars burning somewhere in the observable universe right now. That number is the backdrop against which the question of life becomes almost vertiginous. Current data from exoplanet surveys suggest that roughly 1 in 5 stars of a type similar to our own hosts, an approximately Earth-sized planet, in a zone where liquid water could exist on its surface. Even applying a far more conservative estimate, 1 potentially habitable world for every 5 stars across the entire observable universe produces a total approaching 2 times 10 to the 23rd candidate worlds. That is 20 trillion planets, where the chemistry of life might, in principle, have found purchase. Every smudge in the Cosmos Web mosaic is a galaxy. The barely resolved blobs near the edge of detection, the faint curved arcs stretched by gravitational lensing, the compact bright dots. Each one contains hundreds of billions of the stars in that count. Each of those stars may have worlds circling it in silence, each world with its own geology, chemistry, and unrecorded history extending billions of years. The Cosmos Web image covers a patch of sky 3 times the size of the full moon. It represents roughly 100,000th of the total sky. It is a keyhole. Through that keyhole, we have catalogued nearly 800,000 galaxies. If the rest of the sky holds a similar density, the total visible galaxy count across the full celestial sphere approaches 2 trillion. The image is not a photograph of space, it is a photograph of scale, and what the scale reveals, when you look at how those 2 trillion galaxies are arranged across that space, turns out to be something even more surprising than the numbers themselves. Gravity does not scatter mass randomly across the universe. It organizes, given enough time, even a marginally denser region of space, attracts nearby material, grows denser, pulls more strongly, accumulates more mass, until a galaxy forms, then a group, then a cluster, then a supercluster, woven into a web of interconnected structures spanning distances so vast that light needs hundreds of millions of years to cross them. This process operates simultaneously at every scale, from the smallest galactic halo to the largest continuous structure the observable universe contains. The result has a name: the cosmic web. Dense nodes concentrate thousands of galaxies into gravitational cities where matter has been accumulating since the first billion years after the Big Bang. Connecting those cities, elongated filaments of moderate density carry streams of galaxies between clusters, flowing along invisible channels carved by the underlying dark matter structure. Surrounding the filaments, enormous voids span hundreds of millions of light-years in every direction, regions so depleted of matter that galaxies are almost entirely absent from them, vast, empty caverns in the fabric of the cosmos. Emily Liner of Illinois Institute of Technology described the cognitive adjustment this architecture demands. "If you knew nothing about the structure of the universe," she said, "you might assume galaxies were distributed at random. Stand outside on a clear night, and the stars overhead appear scattered without obvious pattern. Scale that intuition up to the full three-dimensional universe, and you would be comprehensively wrong. Galaxies trace the cosmic web. They cluster where the dark matter web is dense and avoid the regions where it is sparse." This understanding is surprisingly recent. Before the 1980s, many astronomers assumed that galaxies clustered locally but were distributed roughly uniformly across larger scales. Then the first systematic galaxy redshift surveys mapped thousands of galaxies in 3 dimensions and revealed something nobody had seen coming. Walls of galaxies hundreds of millions of light-years long, great voids with almost nothing inside, a foam-like structure that looked, in cross-section, like a bubble bath of cosmic scale. Webb's contribution is the extension of that architecture backward in time. The dark matter map from January 2026 traces the cosmic web to when the universe was approximately 3 billion years old. It shows that the web was already established then, already channeling galaxies into clusters and filaments, already carving voids into the expanding fabric of space. The structures visible in the present-day universe are the mature descendants of what Webb photographs at extreme distance. The cosmic vine, a galaxy filament captured at 2 billion years after the Big Bang, is already on its way to becoming a cluster as massive as any we know today. The protocluster JWST, ID1, caught in the act of formation at 1 billion years after the Big Bang, is a future city of galaxies observed across 12.5 billion years of its own history. We are inside this web. Our galaxy, our entire local group, occupies a node on a filament that connects to larger structures stretching across hundreds of millions of light-years. The universe is not a collection of isolated objects. It is a single continuous structure, 13.5 billion years in the making, and Webb has given us the first clear photograph of its bones. What lives inside those bones is something the telescope was never designed to answer, but the question has never felt more urgent. Think about what it means to look at something far away. The moment you see a distant object, the light reaching your eyes left that place some time ago. This is one of the most profound facts in all of science, and James Webb has turned it into the most powerful archaeological tool humanity has ever built. Light travels at roughly 186,000 miles per second. That sounds impossibly fast until you begin measuring it against the scale of the universe. When you look at the moon on a clear night, you see it as it appeared about 1 1/3 seconds earlier. A small delay, nearly invisible, but stretch that distance and the delay transforms into something breathtaking. The nearest star beyond our own, a red dwarf called Proxima Centauri, sits 4.2 light-years away. The light from it that reaches Earth tonight completed a 4-year crossing of nearly perfect emptiness to get here. During those 4 years, entire political cycles ran their course. Scientific discoveries were made and debated. Children who did not exist when that light departed learned to speak. That star had no knowledge of any of it. It simply kept burning. Go farther still. The Andromeda Galaxy hangs in the northern sky as a faint smear visible to the naked eye on a clear night. The light that falls on your retina from it tonight left its source 2.5 million years ago. At that moment, our ancestors were chipping rocks into tools on the African plains. They had no concept of galaxies, telescopes, or the void they lived inside. That ancient light has been crossing space ever since. It did not wait for us to exist, it simply arrived. Now move to a scale that makes Andromeda feel close. The galaxy MOME Z14, confirmed spectroscopically in May of 2025 at the highest redshift ever measured, is so far away that its light traveled for 13.5 billion years before James Webb intercepted it. When the telescope decoded that signal into an image, it was capturing a galaxy as it appeared when the universe was only 280 million years old. Our solar system did not yet exist. The atoms in every human body had not yet been forged inside any stellar furnace. The Milky Way itself was still assembling its first structures in the dark. The word telescope has begun to mean something larger than it once did. Every image James Webb captures is an archaeological dig through layered time, each stratum more ancient than the last. The Cosmos Web Survey, that catalogued 800,000 galaxies in a single mosaic, was not just counting objects. It was sampling cosmic history at every depth simultaneously, the way a core drilled through ancient ice preserves records of thousands of winters stacked one atop another. Every galaxy in that mosaic is the past itself, arriving here in the form of photons. The scientists studying this data are reading a record unlike anything humans have ever constructed. Every object in a James Webb image is a message dispatched across billions of years by something that no longer looks the way it appears. The galaxies have aged, stars inside them have exploded, new generations have risen. Entire worlds may have formed and ended in the vast interval between when that light departed and when it finally arrived. What you see in every deep field image is a ghost, an extraordinarily precise, scientifically measurable ghost. And the part that deserves a long pause is this. Humanity just built the instrument capable of reading those ghosts with real clarity for the very first time. But knowing the instrument exists is only the beginning. The scale of what it is actually measuring is where the story becomes almost too large to hold. When humans first invented writing, roughly 5,000 years ago, the photon that eventually reached James Webb and became an image of MOME, Z14, had already been traveling for 13,495 million years. It had completed 99.996% of its journey. Ancient Sumerians were pressing symbols into clay tablets in Mesopotamia, while that photon was making its final crossing, oblivious to everything that would one day stand at the end of its path. Go back further. Our solar system coalesced from a spinning cloud of gas and dust roughly 4.6 billion years ago. At that precise moment, the light from MOME, Z14, still had 8.9 billion more years of travel ahead of it. Our star had not yet ignited. Earth had not yet formed. The first oceans did not exist. And that photon was less than halfway through its crossing, flying through an expanding cosmos in perfect silence. This is the kind of number that refuses to feel real no matter how many times you encounter it. Consider the photon's journey as a biography. It originated in a compact galaxy roughly 500 light-years across, blazing with star formation in the infant universe. It escaped its home galaxy into intergalactic space and began billions of years of crossing void, so vast and so empty that the odds of encountering any particle along the way were vanishingly small. While it flew, civilizations of stars rose and died inside the Milky Way. While it flew, the great extinction events of Earth reshaped life on this planet. While it flew, mammals diversified, and one species among them built language, philosophy, and science. Then, one morning in deep space, a telescope intercepted it. James Webb's mirror, hexagonal and golden, and held at 270 degrees below 0 Fahrenheit, gathered that photon together with trillions of others from the same distant source. The telescope's detectors registered the arrival. Software converted the signal into data. Scientists on Earth opened the files and found a galaxy at the edge of observable time. That photon witnessed the entire history of Earth from a distance. It did not participate, it simply traveled, carrying information that no human instrument had any way of receiving until now. This is why researchers describe James Webb with words that feel almost too large for scientific equipment. Pieter van Dokkum of Yale University, when his team confirmed MOME Z14, noted that sharks have existed on Earth for longer than the age of that galaxy at the moment its light departed. He was reaching for any anchor in human experience that could make the scale feel real. Very few succeed at doing that. Every deep field observation plays out this same story at different depths. Some photons in a single James Webb exposure departed when the universe was 300 million years old. Others left when the universe was 2 billion, or 5 billion, or 10 billion years old, all arriving simultaneously, all decoded simultaneously. The mosaic this produces is a history of the cosmos from its youth to the present, compressed into a single image. And inside that history, something is hidden that no one fully expected to find in such abundance. Stand outside on a clear night and look up. The darkness between the stars is full of galaxies, most of them invisible to human eyes, all of them receding from each other on a tide of expanding space. The question of how large the observable universe actually is, and what its size truly implies, sits at the center of modern cosmology. The observable universe is approximately 93 billion light-years across. This number puzzles people immediately. If the universe is 13.8 billion years old, and light travels at a fixed speed, how can we see anything 93 billion light-years away? The answer is that space itself has been expanding the entire time. An object 13.8 billion light-years away, when it emitted the light we now receive, has since been carried by that expansion to a position roughly 46 billion light-years from us today. We see its ancient light, but the object is now far beyond that distance. This is not movement through space. Space itself is stretching. The volume enclosed by the observable universe is staggering, roughly 4.4 times 10 to the 80th power cubic meters. That is the number 4 followed by 80 zeros. Inside this volume lives the structure astronomers have spent the last century trying to map: galaxy clusters, filaments connecting them, enormous voids where almost nothing exists. But here is the detail that quietly changes everything. The observable universe is a sphere defined purely by the speed of light and the age of time. It is a horizon, not a wall. It is exactly like the horizon you see when standing on a beach. The ocean continues past it. You simply cannot see that far from where you stand. There is no scientific reason to believe the universe ends at the edge of what we can observe. Strong theoretical reasoning suggests it continues vastly, perhaps infinitely, beyond regions of space from which light simply has not yet had time to reach us, or regions so distant that the expansion of space carries them beyond our reach permanently, so that their light will never arrive regardless of how long we wait. The Cosmos Webb survey covered roughly 1,000% of the full sky. Inside that tiny window, 800,000 galaxies. Extrapolating to 2 trillion galaxies across the full observable universe is already a number that strains comprehension. But the observable universe is itself only the visible fraction of what may have no edges at all. Every cosmological model James Webb is testing, every distance record it breaks, every early galaxy it finds in the first few 100 million years after the Big Bang, applies only to the portion of reality we can, in principle, observe. Whatever lies beyond the cosmic horizon is by definition beyond our reach, our knowledge, and our instruments. We are map makers who have charted one small district of a city that may extend without limit in every direction. The structures visible to us are extraordinary on their own terms. And those structures, it turns out, are built from something we cannot directly see at all. Most of the universe is invisible. This is a confirmed scientific result, and it is one of the strangest things humanity has ever had to fully absorb. Everything detectable by any instrument ever built, every star, every galaxy, every cloud of glowing gas, and every drifting comet adds up to roughly 5% of the total energy content of the universe. Dark matter accounts for about 27%, invisible to every form of radiation but detectable through its gravitational pull on visible matter. Dark energy accounts for roughly 68%. a property of space itself that drives the universe's accelerating expansion. Even within the visible 5%, the emptiness is almost absolute. The average density of matter in the universe works out to roughly 6 protons per cubic meter. A cubic meter is the size of a large cardboard box. Fill that box with ordinary air, and it contains around 25 trillion molecules. Fill it with the average matter content of the cosmos, and you get 6 protons. The universe, for all its galaxies and stars and visible complexity, is more than 99.9999999% empty space. And yet it does not look empty. The cosmos web mosaic is filled with light. The dark matter map, published in January of 2026, is dense with structure. How can something be simultaneously that empty and that full of complex organization? The answer is clustering. Matter follows the invisible architecture of dark matter filaments, collapsing into dense knots of galaxies while leaving behind enormous voids that can span hundreds of millions of light years in every direction. Those voids are genuine abysses, regions of the cosmos where you could travel for 100 million years and encounter almost nothing. The bright galaxies in every deep field image are the extreme concentrations, the mountain peaks of a landscape that is mostly flat and barren. There is another layer to this emptiness that touches something quietly unsettling. 2 trillion galaxies should, by naive calculation, make the night sky blaze with uniform light. Every direction you look should intersect some distant galaxy. The sky should not be dark. This puzzle, first described formally by the German astronomer Heinrich Olbers in the 1800s, lingered for generations. The resolution is the expansion of space itself. As the universe expands, light from distant galaxies gets stretched to wavelengths too long for human eyes, shifted into infrared and microwave ranges invisible without instruments designed for them. The galaxies are there. Their light is there. We simply cannot detect it without machines built specifically to receive it. James Webb was built precisely for those wavelengths. It has revealed more of what was hidden in the dark than any instrument before it. And what it has revealed in that dark is now raising a question that reaches far beyond the boundaries of astronomy. Here is a number worth sitting with for a moment: 200 million. That is a conservative scientific estimate for the number of technological civilizations that might exist or have existed in the observable universe, built from calculations using galaxy counts, stellar populations, and what we know about the fraction of stars hosting planets in habitable conditions. 200 million civilizations, each separated from the others by distances so vast that a signal traveling at the speed of light between galaxies would take millions of years just to cross the gap. And humanity has found not one signal from any of them. Every galaxy James Webb reveals is a candidate. The Cosmos Webb mosaic contains 800,000 galaxies, each typically holding hundreds of billions of stars, many of those stars hosting planets. Every faint smear of light in that image represents a system of worlds as old or older than our own, built from the same physics, the same chemistry, the same raw materials that produced life here. The James Webb deep fields have sharpened what was already one of the most uncomfortable problems in science. The Italian physicist Enrico Fermi asked it in a single sentence during a lunch conversation in 1950. If intelligent life is so probable across a universe this large, where is everybody? The question was nearly casual at the time. Decades of mounting evidence have transformed it into a genuine scientific mystery, carrying implications for everything from biology to philosophy to long-term human planning. Every new galaxy James Webb finds deepens the silence. Each one is another data point in a distribution that keeps pointing toward the same result. The universe is vast. It has been available for life for billions of years, and nothing has announced itself. There are those who find this silence a relief. If no civilization in 13 billion years has reached interstellar scale, perhaps the barriers to that achievement are higher than we assume. Perhaps no one is coming. Others find the silence the most disturbing fact in science. It has survived every improvement in telescope capability. It survived the discovery of exoplanets by the thousands. It survived the confirmation of complex organic chemistry in places once thought sterile. The silence is durable, and each new image from James Webb renders it louder by contrast. Every blank square of sky in a deep field contains galaxies too faint to resolve, stars too distant to study, worlds too far to examine. And none of them have sent a signal that any human instrument has ever intercepted. They are, as far as all evidence shows, simply there, burning, aging, silent. The question of why leads to answers that none of them make easy. The silence demands explanations, and scientists have offered several. None of them are comfortable to live inside. The first possibility has a name researchers call the Great Filter. The concept proposes that somewhere along the path from simple chemistry to an interstellar civilization lies a barrier so difficult to cross that almost no species manages it. The question that carries real weight is where that filter sits. If the filter is behind us, somewhere in the emergence of complex cellular life, or in the development of multicellular organisms, or in the rise of sustained intelligence itself, then we are extraordinarily rare. The silence would be explained by the fact that we are among the first to have made it through. That possibility, strange as it sounds, is flattering. It makes Earth a near miracle, and human civilization something genuinely precious in a universe that has been trying and failing to produce complexity for billions of years. If the filter is ahead, the implications reverse completely. It would mean civilizations consistently reach a certain threshold of technological capability and then collapse before spreading beyond their home star system. Our current moment, with its accumulating technological risks and global stresses, would look less like a difficult phase and more like the place where the chain typically breaks. The second framework is about distance and time rather than biological rarity. The observable universe is 93 billion light-years across. A civilization in a galaxy 50 million light-years away that began transmitting signals would need to aim precisely toward our location, produce signals strong enough to survive the crossing, and hope we were listening in the right direction at the right moment. Communication between galaxies at light speed takes millions of years. Human civilization has existed for roughly 10,000. The timing problem alone could explain the silence without requiring that life is rare at all. A third possibility that researchers find increasingly plausible is that we are early. The universe at 13.8 billion years old is young by its own standards. It will remain capable of supporting stellar systems for hundreds of billions of years more. Complex life may only now be beginning to emerge at meaningful scale. We might be among the first, rather than a latecomer. Each of these answers carries different weight for what humanity's future should look like. James Webb cannot resolve which one is true, but every image it captures makes the question feel more urgent and less theoretical. Before the wonder calcifies into certainty, it is worth pausing for honest doubt. Science advances through challenge, and cosmology is no exception. The 2 trillion galaxy estimate is a projection, not a direct count. Christopher Consolis and his colleagues at the University of Nottingham built that figure through 3-dimensional modeling of galaxy density across cosmic time, accounting for galaxies too faint and distant for current telescopes to detect directly. The model is sophisticated and well regarded, but it is still a model. The actual number could be higher. It could be somewhat lower if assumptions about faint galaxy formation turn out to need revision. The impossible galaxies problem is real. The gap between what the standard cosmological model predicted and what James Webb found at extreme redshifts is large enough that it cannot be dismissed. However, most working cosmologists are not ready to declare the underlying framework broken. The leading interpretation is that the early universe formed stars faster than models assumed, possibly because the feedback mechanisms that typically slow star formation were less effective in those first few 100 million years. This requires significant adjustment to our models, but may preserve the core structure. Some early distance record claims from the telescope's first years were revised downward after careful spectroscopic follow-up. Objects that appeared extraordinarily distant in photometric data turned out, when measured precisely, to be at lower redshifts. The field has learned to be careful, and the most recent confirmed records come with thorough spectroscopic verification. The most important caveat of all concerns life. Our sample size is 1. We know life exists on Earth. We know of no confirmed life anywhere else. Drawing statistical conclusions about the probability of life across 2 trillion galaxies from a sample of 1 is an exercise in motivated reasoning as much as genuine inference. The honest scientific position is not that life is everywhere, and it is not that we are alone. It is that we simply do not yet know, and the tools capable of beginning to find out are only now coming online. Euclid, launched in 2023, is mapping large-scale structure at scales Webb cannot cover. The Nancy Grace Roman Space Telescope will survey areas far larger than Webb's deepest fields. Ground-based observatories coming online this decade will make atmospheric spectroscopy of distant planets routine. That means we are also at the beginning of an era of revision. What we know now is real. What we think it means is provisional. Holding both truths at once is not a weakness. It is the actual practice of science at its best. Carl Sagan wrote, in the 1970s, that if it is just us in the universe, it seems like an awful waste of space. He was trying to convey a feeling that resists precise measurement, that the scale of the cosmos implies something about its possibilities. He could not have known that half a century later, a telescope floating in deep space would provide the most detailed inventory of that space ever assembled. And he could not have known how deeply the images would intensify rather than resolve the feeling he was describing. The James Webb images do something to people. They are measurements. The Cosmos Webb Mosaic is a scientific catalogue processed through infrared detectors and color mapped to wavelengths human eyes can interpret, but at its foundation, it is a record of actual light from actual galaxies that genuinely exist, billions of them, each containing hundreds of billions of stars. And when you understand what you are looking at, the weight of it lands slowly. 1 galaxy out of 2 trillion, that is our address. The Milky Way, a moderately large spiral roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, 1 of 2 trillion. Within it, 1 ordinary star among those hundreds of billions. Around that star, 1 planet at the right distance, with the right chemistry, producing life that eventually looked upward and asked what else existed. The dark matter map published in January of 2026 revealed something that sits quietly at the center of all of this. The universe is organized, structured along invisible filaments spanning billions of light-years. Clusters of galaxies connected by threads of lower density, surrounded by voids that stretch for hundreds of millions of light-years. The architecture is hierarchical, intricate, and consistent across the entire observable universe. A universe this organized does not look like an accident. Whether that observation carries deeper meaning is a question science cannot yet answer and may never be equipped to answer definitively. But the fact of the organization, the improbability of a cosmos that is simultaneously this vast and this precisely structured, carries a quality that the word coincidence struggles to contain. James Webb was built because a species on 1 planet, around 1 ordinary star, in 1 of 2 trillion galaxies, decided that understanding the universe was worth $10 billion and decades of collective human effort. That choice says something about consciousness that has no known equivalent anywhere else in the cosmos we can observe. And what consciousness has found, looking back across 13.5 billion years of cosmic history, is that the more clearly we see, the larger and more beautiful the mystery becomes. There is a moment described by Diana Scognamiglio of the NASA Jet Propulsion Laboratory that captures something essential about working at the frontier of knowledge. In May of 2025, she showed a comparison slide at a scientific collaboration meeting, placing the new James Webb dark matter map alongside the best previous map of the same region. The room went quiet. Then people started clapping. She described it as recognition, not politeness. A room full of scientists, seeing the shape of an old question answered with new clarity. That moment is a small window into the story this documentary has been building across 30 chapters. James Webb was not built simply to produce beautiful images. It was built to answer questions that had been accumulating for a century. How did the first galaxies form? How did the cosmic web emerge from the smooth plasma of the early universe? What happened in the first few 100 million years after the Big Bang? How common is the chemistry that produces complex molecules? The telescope has provided partial answers to all of these, and in doing so has generated more new questions than it has resolved old ones. That is precisely how science moves forward. The galaxy MOME Z14, 13.5 billion light-years away, existed and blazed with star formation before the Milky Way had taken shape. The protocluster JWST, ID1, actively assembling 12.7 billion light-years away, showed that the largest structures in the universe were building themselves a billion years earlier than models predicted. The Cosmos Web survey revealed 800,000 galaxies in a patch of sky, 3 times the size of the full moon, and that patch is 1,000% of the total sky. The dark matter map made the invisible scaffolding of the cosmos visible with genuine resolution for the first time. Each of these is an opening, a door left ajar. The observable universe spans 93 billion light-years. It contains 2 trillion galaxies and roughly 10 septillion stars. More stars than there are grains of sand on every beach and desert on the surface of this planet combined. At a conservative estimate of 1 Earth-sized world per 5 stars, the number of potentially habitable worlds in the observable universe reaches into the hundreds of millions of trillions. And we are here, on one of them. Using instruments assembled from materials forged in the cores of dead stars, launched into space on rockets built by mathematicians and engineers, operated by scientists who devoted careers to constructing one clear picture of what exists. Looking back at all of it, trying to understand what it means, James Webb gathers light that has been traveling since before Earth existed and turns it into knowledge. It watches galaxy clusters being born. It finds oxygen in galaxies that formed when the universe was barely 2% of its current age. It traces the invisible architecture of dark matter across billions of light years. Every image it sends back is a fact about a universe that had no obligation to be comprehensible. And yet here it is. Partial, imperfect, provisional, and genuinely comprehensible. The same laws that govern the formation of MOME Z14 govern the computer reading its data and the mind interpreting that data and the planet turning quietly beneath it all. That connection between a galaxy 13.5 billion light-years away and a species young enough to still be surprised by what it finds is the most astonishing thing the telescope has ever captured. We are not outside the universe looking in at something foreign. We are the universe looking back at itself.